Our goal for this project was to study failure in ski poles in order to learn about how safety factors play a role in the design process. We don't expect them to fail under typical static loading, so we decided to frame our analysis around static failure when cracks are present and fatigue failure from cyclic loading.
For this analysis, we chose the weight of the skier, the speed at which they're skiing, and the temperature of the surrounding environment as the three main contributing factors to the loading scenario of the ski pole. There are many more that we could use, but we thought that these three summed up the scenario as best as possible. The weight of the skier will determine the axial force felt by the pole in use. The speed of skiing will dictate the momentum, and thus those perpendicular forces applied to the pole when it comes in contact with the surrounding environment. And we finally chose the surrounding temperature because that'll influence the stress felt by the pole through the unique material properties tied to aluminum, which is the choice of material for most ski poles and what we chose for this analysis.
So geometrically, on our free body diagram, you can see we went with a length of 1.35 meters for our pole length, an outer radius of 7 millimeters, and an inner radius of 6.2 millimeters. This means the pole has a thickness of 0.8 millimeters, which we figure we can model as a thin walled cylinder. The angle of the ski pole is more for the framing of the problem. As far as calculations, we use the x prime y prime axes, which align axially with the ski pole. As far as forces go, our 445 Newton axial load was based off the average male weight of 89 kilograms. Half of that is about 45, and that's about 445 newtons. The moment was a little more subjective, but we figured 6.75 Newton meters would be a fair estimate. Not pictured is our crack size, which we approximated as 4 millimeters. Because the tip of the ski pole is almost always in snow, it was safely assumed for this analysis that it could not support a torsional force. Additionally, while it is possible for transverse shear force to be present from skiing, it was assumed that for most cases the shear force would be insignificant compared to the other forces present, thus it was neglected. This is justifiable because it is most effective to apply a force axially on a ski pole while skiing. Therefore, with good form, any transverse shear should be negligible. Due to how the human hand and the handle of the ski pole interact, it was assumed that a moment would be present at the handle. Again, because it is assumed that the skier has good form, the moment was assumed to be relatively small compared to the axial force.
In order to analyze the static failure due to crack propagation, it was assumed that the pole could be modeled as a sheet with a crack in the middle, since this is the type of analysis that we are equipped to handle. Using this assumption, the width of the sheet was equivalent to the circumference of the outside of the pole, and the length and the thickness remained the same. Similarly, assumptions were made in order to analyze fatigue failure based on what we are equipped to solve. Although we know our loading scenario will not be perfectly repeated over and over, we assumed that over the course of many cycles, this loading is essentially an average, and as such, treated it as if it was replicated for every cycle. We also assumed that the combined loading acts in the same frequency and phase with each other due to the nature of the use of a ski pole.
Here are the equations that we use for both our static failure and our fatigue failure. So for our static failure, after calculating the stresses, we found the alpha value for the geometry of our flat sheet, then found our F. This helped us calculate our stress intensity factor, which then helped us find our safety factor when using our K1C value. For our fatigue failure, after finding the stresses, we found the mean and the amplitude of the stresses, and then found the completely reversible stress amplitude. We used this to calculate the fatigue life of our component. We can justify these equations because in our fatigue model, we use the modified Goodman approach, which is reasonable for brittle materials and conservative for ductile materials. We also calculated sigma AR for fully reversible stress and used this in our SN relationship. In our fracture, we made sure that LEFM is met, and so that was an appropriate model to use for our fracture failure.
Since we calculated a safety factor against static failure of 19.1 and over 200 billion cycles before fatigue failure, we wouldn't expect to ever see ski poles fail, but that is not the case. There are limitations to our results based on the assumptions we made. By modeling ski poles as thin-walled cylinders, we erase stress raises at the handle and other locations from our consideration. Additionally, ski poles often bend or dent. These bends and dents could contribute to the overall state of stress, even though we were unable to consider them for this analysis. Based on our research on material properties, we neglected temperature effects. However, we realized that cycling between extreme cold and room temperature could affect the life of the part. A more conservative approach would take all these things into account, but since breaking a ski pole is more of an inconvenience than a tragedy, we believe our assumptions are reasonable.